There's a moment that astronauts talk about, the moment when they first look out the window of their spacecraft and realize they're about to step outside. They've trained for years. They know intellectually what's coming, but no amount of preparation changes the visceral understanding that settles in as they check their suit pressure one final time. Because outside that airlock isn't just cold, it's not like standing on a frozen lake or at the peak of a mountain in winter. It's not even like the coldest place on Earth, the depths of Antarctica or the high desert of the Atacama. What awaits outside is something fundamentally different. It's an environment so foreign to human experience that the words we use to describe it feel inadequate. Space is cold, devastatingly, incomprehensibly, absolutely cold. The question is, why? Why is the vacuum of space so cold when it's mostly empty? How can nothing be so cold? And what does that temperature actually mean when there's almost no matter there to transfer heat? The answer requires us to rethink what we mean by heat, cold, and temperature itself. It requires us to understand the universe at scales from the atomic to the cosmic. It requires us to grapple with the fact that the very fabric of space itself carries temperature, energy imprinted from the birth of the universe. Let me start with the most basic question. What does temperature actually mean in space? On Earth, when we talk about temperature, we're talking about how fast atoms and molecules are moving. A hot cup of tea has molecules vibrating rapidly. That vibration is what we perceive as heat. A cold ice cube has molecules moving slowly. Temperature is fundamentally about motion. But here's where it gets weird. In space, there are barely any molecules at all. The vacuum of space contains maybe 1 atom per cubic centimeter. Sometimes fewer. In the best laboratory vacuums we can create on Earth, we can remove almost all the air, but even then, we have far more atoms than exist in the same volume of interstellar space. So if there are barely any atoms to vibrate, if there's almost nothing there, how can space have a temperature? The answer involves understanding that temperature isn't just about the motion of atoms. Temperature is also encoded in the radiation that passes through space. Every bit of radiation, every photon, carries energy, and that energy is associated with a temperature. In the 1960s, two scientists named Arno Penzias and Robert Wilson were working at Bell Labs trying to detect faint radio signals from space when they kept running into this persistent noise in their instruments. No matter what they did, they couldn't eliminate it. They tried everything, checked their equipment, looked for sources of interference, even considered that pigeons nesting in their antenna might be the culprit. Eventually, they realized the noise wasn't coming from their equipment or any terrestrial source. It was coming from space itself. More specifically, it was the echo of the Big Bang itself, the cosmic microwave background radiation, CMB. The faint light that has been traveling through the universe since just 380,000 years after the universe began. This radiation has a temperature. Scientists can measure it. And that temperature is about 2.7 Kelvin, which is about 2.7 degrees above absolute zero. This is why space is cold, not because the atoms in space are moving slowly, though in many cases they are, but because the radiation filling space, the photons traveling through the vacuum, correspond to a temperature of just 2.7 Kelvin. Absolute zero is minus 273.15 degrees Celsius. 2.7 Kelvin is minus 270.45 degrees Celsius. This is cold beyond what most humans have ever experienced. But there's a complication, and it's an important one. The vacuum of space isn't uniformly cold. There are pockets of warmth, islands of heat in the cosmic cold. Near a star, for instance, the radiation from that star heats up nearby objects. An astronaut on the daylight side of the International Space Station can actually get too warm. The intense radiation from the sun heats their suit faster than the passive cooling systems can handle. They have to turn on active cooling, using water circulation inside their suit to shed the excess heat. Meanwhile, on the night side of the same space station, it's brutally cold. The spacecraft is radiating its heat away into the void, and there's no star to provide warming radiation. Temperatures drop to minus 150 degrees Celsius or colder. This is the paradox of space. It's simultaneously radiating intense heat from stars and radiating that heat away into the cold void of space. Objects in space can be simultaneously burning hot on one side and freezing on the other. The coldest places in space are the places farthest from any star, where the only radiation reaching them is the cosmic microwave background. In deep space, far from any solar system, objects left alone would eventually cool to 2.7 Kelvin. But before we go further into the cold of space, let me explain what makes space cold in the first place. Why is the cosmic microwave background only 2.7 Kelvin? Why isn't space warmer? The answer involves the expansion of the universe and a concept called redshift. When the universe began with the Big Bang, it was incomprehensibly hot. At the earliest moments, there were no atoms, no molecules, just pure energy in the form of radiation. This radiation had enormous energy, corresponding to temperatures of billions of degrees. As the universe expanded, something remarkable happened. The space itself stretched, which meant the wavelength of the radiation stretched too. Imagine a light wave traveling through space. As space expands, that wave gets spread out. Its wavelength gets longer, its frequency gets lower, and its energy decreases. This is called redshift. The same photons that had enormous energy when the universe was young now have far less energy. That reduction in energy corresponds to a lower temperature. After 13.8 billion years of expansion, those ancient photons from the Big Bang have been redshifted so much that they now correspond to only 2.7 Kelvin. This is profound. It means that the temperature of the cosmic microwave background is a direct measurement of how much the universe has expanded since the Big Bang. It's like a cosmic thermometer that tells us about the entire history of the universe. Now let's talk about what happens to objects in this cold environment. How does an astronaut in a spacesuit actually experience the cold? This is where things get fascinating, because the cold of space doesn't work the way cold works on Earth. On Earth, if you stand outside in the freezing cold, you lose heat through three mechanisms: conduction, convection, and radiation. Conduction is direct contact. If you touch a piece of ice, heat flows from your hand to the ice. The molecules in your hand collide with molecules in the ice, transferring kinetic energy, and you feel cold as your hand loses heat. Convection is heat transfer through air movement. Cold wind strips away the warm air layer surrounding your body and replaces it with frigid air. This is why wind chill makes cold weather feel colder than the temperature suggests. Radiation is heat transfer through electromagnetic waves. Every object emits infrared radiation, and cold objects emit less than hot objects. If it's cold outside, you're radiating more heat than you're receiving back. In space, conduction and convection are almost impossible. There's essentially no air for convection. There are almost no atoms for conduction to occur. An astronaut's suit isn't losing heat through these mechanisms. Instead, an astronaut loses heat almost entirely through radiation. Their suit emits infrared radiation into the void, and because there's nothing to emit radiation back to them except the distant cosmic microwave background and any starlight, The net result is heat loss. This might seem like it would be manageable, just radiation, but it's actually quite efficient. Objects in space can radiate heat away very quickly. This is why the thermal control systems on spacecraft are so crucial. Astronauts inside a suit generate heat from their metabolism, and their suit has to radiate that heat away into space or they'll overheat. Modern spacesuits have passive radiators, flat surfaces that radiate heat efficiently. They also have active cooling systems that circulate water to absorb metabolic heat and then radiate it away through radiators on the outside of the spacecraft. In fact, one of the most dangerous scenarios for an astronaut is a failure of the cooling system. They'll generate heat faster than it can be radiated away, and their suit temperature will rise. They could literally overheat to death in the middle of the freezing vacuum of space. Ironically, the primary danger to an astronaut isn't freezing. Modern spacesuits are well insulated. The danger is the mismatch between how fast heat is generated and how fast it can be radiated away when the cooling system fails. There's another factor that makes the vacuum cold in a unique way, and it's related to how heat and pressure interact. In everyday life, we experience pressure from air. This air pressure isn't just about keeping us from imploding, though it does that. It's also about how heat and energy are distributed. When a gas is compressed, it heats up. When it expands, it cools down. This is because the compression does work on the gas, adding energy, which increases the temperature. In the vacuum of space, this expansion process has already happened to an extreme degree. Any gas that exists there has expanded to the point where it's incredibly dilute and cold. But there's something even more subtle happening. The vacuum itself, the empty space, acts as an insulator. It prevents the transfer of heat between objects. This is why thermos bottles have a vacuum layer. It prevents heat from conducting or convecting across the gap. In space, this insulation is perfect. There's nothing to conduct heat. There's nothing to convect. Only radiation remains. Now, I want to talk about the coldest places in the universe because space being cold isn't uniform. Some places are far colder than others. The cosmic microwave background provides a baseline temperature of about 2.7 Kelvin throughout the universe. But local objects can be much colder or much warmer. Very cold objects might be clouds of gas and dust in interstellar space, far from any star, that haven't been heated by radiation. These might be only a few degrees above absolute zero. The Boomerang Nebula, a protoplanetary nebula about 5,000 light-years away, has been measured at approximately 1 degree Kelvin, even colder than the cosmic microwave background. How is this possible? The Boomerang Nebula is rapidly expanding. As the gas expands, it cools. This is the same principle that makes a refrigerator work. By expanding a gas, you can cool it below the temperature of its surroundings through adiabatic expansion. The Boomerang Nebula is expanding so rapidly that it has cooled to nearly absolute zero. It's one of the coldest known objects in the universe. But here's what's remarkable. Even at 1 Kelvin, this nebula isn't at absolute zero. Absolute zero, 0 Kelvin, or minus 273.15 degrees Celsius, is the temperature at which all molecular motion theoretically stops. It's a theoretical limit. According to our understanding of physics, you can't actually reach absolute zero. You can get arbitrarily close, but you can't get there. The Boomerang Nebula is extraordinarily close to absolute zero. It's 1 Kelvin. At this temperature, the thermal energy is almost entirely gone. The gas and dust particles are moving at their slowest possible speeds. It's as close to absolute stillness as the universe allows. On the other end of the spectrum, the cores of stars can reach millions of degrees. The cores of the most massive stars can reach billions of degrees before they collapse and explode as supernovae. These are the hottest places in the universe we're aware of, but the average temperature of space, excluding these local variations, is about 2.7 Kelvin, the temperature of the cosmic microwave background. Let me talk about why this matters for our understanding of the universe and how scientists discovered it. Before Penzias and Wilson detected the cosmic microwave background, there was a long-standing debate about the origin of the universe. One school of thought, called the steady-state theory, proposed that the universe had always existed in roughly its current form, with new matter being continuously created to maintain a constant average density. Another school of thought, called the Big Bang theory, proposed that the universe had a definite beginning and had been expanding ever since. This theory made a remarkable prediction. If the universe began hot and has been expanding ever since, there should be a faint glow of radiation from that ancient heat, redshifted by billions of years of expansion. The Big Bang theory predicted that this radiation should exist, should be very uniform in all directions, and should have a temperature corresponding to the expansion history of the universe. When Penzias and Wilson detected the cosmic microwave background, it was a triumph for the Big Bang theory. Here was direct evidence of that ancient radiation. Here was proof that the universe had a hot beginning. But what's profound about the CMB isn't just that it proved the Big Bang, it's that it's telling us that space itself has a temperature. The vacuum of space isn't just empty, it's filled with radiation from the Big Bang. Space itself is cold. This has deep implications. If space has a temperature, then space has entropy. Space has thermodynamic properties. In a very real sense, the universe itself is a thermodynamic system. Now let me talk about how humans have come to understand and work with the extreme cold of space. The first humans to experience the vacuum of space were astronauts in the 1960s. Yuri Gagarin's flight in 1961 was the first human spaceflight, but it was a suborbital flight. He didn't stay in space long. The first astronaut to orbit the Earth and return was John Glenn in 1962. He flew in the Mercury Atlas 6 spacecraft. Even in this early spacecraft, they had thermal control systems, though they were relatively primitive by modern standards. The first spacewalk, a human stepping outside a spacecraft into the vacuum of space, was Alexei Leonov in March 1965. He was outside for only about 12 minutes, tethered to his spacecraft the entire time. His spacesuit was pressurized with pure oxygen at low pressure, which was actually dangerous because it increased fire risk, but it was thought to be necessary at the time. The Cold War space race drove enormous advances in spacesuit technology. Both the Soviet Union and the United States knew that whoever could send humans into space more reliably, more safely, and for longer duration would have a technological advantage. The Apollo program, which sent humans to the moon, required spacesuits that could function in the extreme cold of the lunar surface, where temperatures can drop to minus 170 degrees Celsius in shadow, while simultaneously protecting against the extreme heat of direct sunlight, about 120 degrees Celsius. The spacesuits for the Apollo program were engineering marvels. They had multiple layers of different materials: outer shells to protect against micrometeorite impacts, insulation layers, pressure suits to maintain the astronauts' body pressure, and liquid cooling garments that circulated water to remove metabolic heat. One particular concern was radiation. In space, outside the protection of Earth's magnetic field, astronauts are exposed to cosmic rays and solar radiation. The Apollo spacesuits provided some protection, but not complete. This is why astronauts on the moon spent limited amounts of time on the surface. Interestingly, one of the major concerns during the Apollo program wasn't the cold so much as protecting the astronauts from radiation and dust. The lunar dust was abrasive and got into everything. It wasn't cold in the way we think of cold on Earth. It was an alien environment with its own set of extreme challenges. As spaceflight continued and humans began spending longer periods in space, on Skylab in the 1970s and Mir in the 1980s and 1990s, spacesuits evolved. By the time the International Space Station began operations in 2000, spacesuit technology had advanced tremendously. Modern extravehicular activity, EVA, suits, also called spacesuits, are incredibly sophisticated. They provide pressure, temperature regulation, oxygen, carbon dioxide removal, and protection from radiation and micrometeorite impacts. The temperature management is particularly interesting. A human at rest generates about 100 watts of heat. A human doing physical activity might generate 200 watts or more. In space, where radiation is the only way to lose heat, the suit has to be able to radiate at least that much heat or the astronaut will overheat. Modern suits use liquid cooling garments, essentially water-cooled undergarments that the astronaut wears. The water is circulated through tubing in the garment, absorbing heat from the astronaut's body. The water then flows to radiators on the outside of the suit, or on the spacecraft, where it radiates the heat into space. The effectiveness of these radiators is remarkable. In the vacuum of space with nothing to interfere, objects can radiate heat very efficiently. An astronaut's suit radiators can handle several hundred watts of heat output. But this also means that spacesuits are a careful balance. If the astronaut generates too much heat, the cooling system can't handle it. If the astronaut generates too little heat, or if the cooling system fails, the astronaut will lose heat too quickly and could become dangerously cold. In a failed cooling system scenario, an astronaut might actually freeze. Not immediately. It takes time to lose core body heat. But eventually, without active cooling or passive insulation, an astronaut in the cold of space could become hypothermic. This is why modern spacesuits have backup systems. They have redundant cooling loops. They have passive radiators that can handle heat loss through radiation, even if the active cooling fails. The evolution of spacesuits is a testament to human ingenuity in the face of an alien environment. We've learned to live and work in the cold of space by understanding the physics of heat transfer, insulation, and radiation. But spacesuits are only a short-term solution. Humans can't spend years in spacesuits. To truly expand into space, to colonize other worlds, we'll need habitats. Enclosed environments where humans can live and work without spacesuits. Creating habitats in space means solving the problem of temperature control. Inside a spacecraft, all the heat generated by the crew, the equipment, and the electronics has to be radiated away into space. This is done with radiators, large panels that emit infrared radiation into the void. The International Space Station has enormous radiators taking up much of the station's surface area. These radiators are crucial for maintaining a livable temperature inside the station. As we think about establishing bases on the Moon or Mars, temperature control will be one of the primary engineering challenges. On the Moon, it's the extreme swings in temperature, from 120 degrees Celsius in sunlight to minus 170 in shadow. On Mars, it's the pervasive cold, with temperatures typically ranging from -50 to -120 degrees Celsius. For Mars, creating habitats means either heating them with internal heat sources or solar power, and radiating the excess heat through radiators or insulating them extensively to maintain temperature. For the Moon, because of the extreme swings, the engineering is more complex. It might be easier to site habitats underground, where the temperature is more stable than on the surface. These engineering challenges are solvable. They require power, smart materials, and good engineering, but they're not fundamental impossibilities. Now, let me talk about the historical understanding of cold and temperature and how that's changed over time. For most of human history, temperature was understood only through sensation. Something felt hot or cold, and that was about all we knew. There was no way to quantify it. In the 1600s and 1700s, scientists began inventing thermometers. Galileo is sometimes credited with inventing the first thermometer in the early 1600s, though he called it a thermoscope and it wasn't really practical. The thermometer that became useful was developed over the 1600s by scientists like Robert Boyle and Guillaume Amentons. They noticed that gases changed volume with temperature in a predictable way. In 1702, Guillaume Amenton proposed a temperature scale based on the expansion of gases. He proposed that there was a minimum temperature, a point where a gas would have zero volume. He calculated this to be at about -240 degrees Celsius, which is actually remarkably close to absolute zero, -273.15 degrees Celsius. This was a remarkable insight. Based purely on the behavior of gases, Amentons had deduced that there must be a lowest possible temperature. In the 1750s, Anders Celsius and Carl Linnaeus developed the Celsius temperature scale, with 0 degrees as the freezing point of water and 100 degrees as the boiling point. In 1848, Lord Kelvin, William Thomson, developed an absolute temperature scale with 0 Kelvin at what was theoretically the lowest possible temperature. He based this on the gas laws and the insights of scientists like Amentons. It wasn't until the late 1800s that scientists could actually achieve temperatures approaching absolute zero. James Dewar and others developed techniques for liquefying gases. In 1877, Raoul Pictet and Louis Cailletet independently liquefied nitrogen. In 1908, Heike Kamerlingh-Onnes liquefied helium, reaching temperatures of about 4 Kelvin. This opened up a new field of physics, low-temperature physics. Scientists found that materials had remarkable properties at extremely low temperatures. Some materials became superconductors with 0 electrical resistance. Others became superfluids, flowing without viscosity. But the ultimate frontier was reaching lower and lower temperatures. It wasn't until the 1960s that we discovered the cosmic microwave background and realized that space itself has a temperature of about 2.7 Kelvin. This was profoundly humbling. No matter how cold scientists could make things in laboratories, space was naturally colder. The cosmic microwave background has been measured with extraordinary precision. Satellites like COBE, WMAP, and Planck have measured the temperature of the CMB to incredible accuracy. The latest measurements show that the cosmic microwave background has a temperature of 2.72548 Kelvin, with uncertainty in the 5th decimal place. What's remarkable about this precision is that it's telling us something profound about the universe. The temperature of the CMB depends on the expansion history of the universe. By measuring it precisely, we're measuring the universe's expansion. Scientists have found that the expansion of the universe isn't just uniform, it's accelerating. This acceleration is driven by dark energy, a mysterious form of energy that makes up most of the universe. The discovery that the universe's expansion is accelerating was so unexpected that it won the Nobel Prize in Physics in 2011. The cosmic microwave background is also telling us that the universe is very uniform. In every direction, the temperature is almost identical to 1 part in 100,000. This uniformity is one of the most profound discoveries about the universe. It also suggests that the universe is infinite, or at least far larger than the observable universe. If the universe were small and finite, we'd expect to see variations in the cosmic microwave background corresponding to different regions of the universe. The fact that it's so uniform suggests that we're only seeing a tiny part of the universe. Now, let me talk about what the cold of space means for life and the search for extraterrestrial life. Life, as we know it, is based on liquid water and complex chemistry. Water freezes at 0 degrees Celsius, and at these temperatures, chemical reactions slow dramatically. At the temperatures of space, 2.7 Kelvin, water is solid ice. In fact, below about 45 Kelvin, water becomes a glass-like solid, no longer crystalline ice, but an amorphous solid. At these temperatures, most complex molecules are frozen. DNA would be frozen solid. Proteins would be inactive. The chemistry of life, as we know it, can't happen. However, there's something remarkable happening in the cold clouds of dust and gas in interstellar space. Despite the incredibly low temperatures, complex organic molecules are forming. In giant molecular clouds, regions of space where hydrogen gas has accumulated to high density, astronomers have detected hundreds of different organic molecules. These include molecules like methanol, acetaldehyde, formic acid, and even amino acids. How can these complex molecules form in the cold? The answer involves cosmic rays, high-energy particles from space that continuously bombard these clouds. When a cosmic ray hits a molecule, it can break it apart and recombine it in new ways. The radiation from distant stars also helps. Additionally, the surfaces of dust grains in these clouds can catalyze chemical reactions. Molecules can stick to the dust grain surface, move around, and react with each other. So even in the cold of interstellar space, chemistry is happening. Complex molecules are forming. The cold isn't an absolute barrier to chemistry, though it slows things down enormously. This is relevant to the search for life in space. While life probably can exist at 2.7 Kelvin, it might exist at the temperatures of other environments, like the subsurface oceans of icy moons. Europa, one of Jupiter's moons, is covered in ice. But beneath the ice is believed to be a liquid water ocean, kept warm by tidal heating from Jupiter's gravity. Enceladus, one of Saturn's moons, also has a subsurface ocean. On these icy worlds, at the interface between the cold ice surface and the warmer liquid water below, life might exist. The water would be liquid, allowing chemistry. There might be energy sources from chemical reactions or from heat. The cold of space is a challenge for life, but it's not an absolute barrier. Life is remarkably adaptable, as far as we can tell. Let me dive deeper into the physics of temperature, because understanding what temperature actually is will help us understand why space is so cold. In the microscopic world, everything is in motion. Atoms vibrate. Electrons orbit nuclei. Molecules rotate and translate. Temperature is a measure of this average kinetic energy. In a hot object, atoms and molecules are moving fast. They're vibrating vigorously. They're colliding with each other frequently. When you touch a hot object, you're experiencing rapid collisions between the molecules in your hand and the molecules in the hot object. In a cold object, atoms and molecules are moving slowly. There's less kinetic energy. When you touch a cold object, you're experiencing slower collisions. At absolute zero, 0 Kelvin or minus 273.15 degrees Celsius, all molecular motion theoretically stops. The kinetic energy is zero. This is the theoretical minimum temperature. But here's something fascinating. Quantum mechanics tells us that absolute zero is impossible to achieve. According to quantum theory, there's always some residual motion, some zero-point energy, even at absolute zero. This was predicted by quantum mechanics and has been experimentally verified. When scientists cool materials to the lowest temperatures ever achieved, we're talking milledegrees Kelvin, 1,000 times colder than the cosmic microwave background, they can still detect residual motion. The implications are profound. The universe can never reach perfect stillness. There's always something happening, always some motion, always some activity. The cold of space is the closest the universe gets to stillness, but it's not perfect stillness. Now let's talk about the thermodynamics of space and why the cosmic microwave background exists. Thermodynamics is the study of heat and energy flow. The laws of thermodynamics are among the most fundamental laws in physics. The first law of thermodynamics states that energy cannot be created or destroyed, only converted from one form to another. The total energy of a closed system is constant. The second law of thermodynamics states that entropy, disorder, always increases in a closed system. This is sometimes called the arrow of time. It's why eggs break, but broken eggs never spontaneously reassemble. It's why hot things cool down, but cold things never spontaneously become hot. It's why the universe evolves in a particular direction through time. The third law of thermodynamics relates entropy to temperature and states that as temperature approaches absolute zero, entropy approaches zero. The colder something is, the more ordered it is. These laws, particularly the second law, have profound implications for the universe. When the universe was born with the Big Bang, it was in an incredibly ordered, incredibly low entropy state. All the energy was concentrated in an infinitely dense point. As the universe expanded, it became more disordered, more chaotic. Entropy increased. The cosmic microwave background is a direct consequence of this. As the universe expanded and cooled, the radiation that filled it was stretched and redshifted. The entropy of the universe increased. The cosmic microwave background today represents the current state of the universe, a very cold, very disordered system with very high entropy. In the distant future, if the universe continues to expand forever, it will become increasingly cold and increasingly disordered. Eventually, it will reach a state called heat death, where all usable energy has been exhausted and no work can be done anywhere in the universe. The cold of space is thus intimately connected to the second law of thermodynamics and the evolution of the universe. Now let me talk about heat transfer in more detail, because this is crucial to understanding why space is so cold. There are three mechanisms by which heat can be transferred: conduction, convection, and radiation. Conduction is the transfer of heat through direct contact. When two objects of different temperatures touch, heat flows from the hot object to the cold object. Microscopically, this is atoms and molecules colliding and transferring kinetic energy. Different materials conduct heat at different rates. Metals conduct heat very efficiently. Wood and plastic conduct heat poorly. This is why a metal spoon in a cup of hot tea gets hot quickly, but a wooden spoon stays cool. The rate of heat conduction depends on the temperature difference, the surface area, the distance over which heat must travel, and the thermal conductivity of the material. Mathematically, it follows Fourier's law of heat conduction. Convection is the transfer of heat through the bulk motion of fluids, liquids, or gases. When a fluid is heated, it expands and becomes less dense. The less dense fluid rises while cooler, denser fluid sinks. This creates a circulation pattern. Convection is what happens when you heat water in a pot. The water at the bottom gets hot, expands, rises, cools at the top, sinks, and the cycle continues. In space, convection is impossible because there's no fluid, there's no air to circulate. This is one reason why thermal control in space is different from thermal control on Earth. Radiation is the transfer of heat through electromagnetic waves. Every object emits electromagnetic radiation in proportion to its temperature. At room temperature, objects emit primarily infrared radiation, which is invisible to human eyes, but can be detected with infrared cameras. The amount of radiation emitted by an object depends on its temperature raised to the fourth power. This is called the Stefan-Boltzmann law. A small increase in temperature results in a much larger increase in radiation. The wavelength of radiation also depends on temperature. The hotter something is, the shorter the wavelength of the radiation it emits. The sun, with a surface temperature of about 5,800 Kelvin, emits primarily visible light. An object at room temperature emits primarily infrared radiation. A cold object at 2.7 Kelvin emits primarily microwave radiation. In space, radiation is the only way heat can be transferred between objects. Because there's no air for convection and no direct contact for conduction, heat must be radiated away. This has profound implications for spacecraft and astronauts. A spacecraft generates heat from the people inside, the equipment, the electronics. This heat must be radiated away through radiators on the exterior of the spacecraft. The efficiency of a radiator depends on its temperature and its emissivity. The warmer the radiator is, the more heat it radiates. Radiators are typically painted black or specially treated to have high emissivity in infrared wavelengths. An astronaut in a suit generates heat from metabolism. This heat must be radiated away through the suit's radiators or through active cooling systems that circulate fluid to absorb heat and radiator it away. The balance between heat generation and heat loss is critical. Too much heat generation and the astronaut overheats. Too little heat loss and the astronaut freezes. Now let me discuss the discovery and study of the cosmic microwave background in detail because it's the key to understanding why space is cold. The discovery of the CMB by Penzias and Wilson in 1964 was actually accidental. They were trying to measure radio emissions from the Milky Way, but they kept finding this persistent noise in their instruments. They tried everything to eliminate the noise. They checked their equipment. They looked for sources of electromagnetic interference. They even considered that pigeon droppings on their antenna might be causing the problem. There were indeed pigeons nesting there. Nothing worked. The noise was always there, no matter what they did. Eventually, they learned that other physicists had predicted that such radiation should exist as a consequence of the Big Bang theory. Robert Dicke and his colleagues at Princeton had even started building an antenna to detect it when they heard about Penzias and Wilson's discovery. The noise that Penzias and Wilson had detected was indeed this predicted radiation, the cosmic microwave background. Their discovery was so important that they won the Nobel Prize in Physics in 1978, along with Arno Penzias and Robert Wilson. After the initial discovery, scientists realized that the cosmic microwave background could teach them an enormous amount about the universe. In 1989, NASA launched the Cosmic Background Explorer, COBE, satellite to measure the cosmic microwave background with unprecedented precision. COBE found that the cosmic microwave background is remarkably uniform. In every direction, the temperature is essentially the same, about 2.72548 Kelvin. But COBE also found tiny variations, tiny ripples in the temperature. These variations are incredibly small, about 1 part in 100,000, but they're crucial. These tiny temperature variations correspond to the seeds of galaxies and clusters of galaxies. The slightly warmer regions in the early universe had slightly higher density. Gravity amplified these tiny differences, and over billions of years, they grew into the galaxies and clusters we see today. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP, to measure the cosmic microwave background with even higher precision. WMAP created detailed maps of the cosmic microwave background. Scientists could see the patterns of the temperature variations across the entire sky. These patterns encoded information about the geometry of the universe, the composition of the universe, and the expansion history of the universe. In 2009, the European Space Agency launched the Planck satellite, which achieved even higher resolution and precision. Planck's measurements revealed that the universe is about 13.8 billion years old. It also showed that the universe's composition is about 5% ordinary matter, atoms, stars, galaxies, 27% dark matter, mysterious substance that doesn't emit light but has gravity, and 68% dark energy, mysterious form of energy causing the expansion to accelerate. These measurements of the cosmic microwave background have revolutionized our understanding of the universe. The temperature of the CMB is not just a curiosity. It's a fundamental property of the universe. It's the temperature at which the universe has cooled due to billions of years of expansion. Now let me talk about extremophiles and the possibility of life in extreme cold. For a long time, scientists thought that life could only exist in a narrow range of temperatures, roughly from freezing point to about 50 degrees Celsius. But in recent decades, scientists have discovered extremophiles, organisms that thrive in extreme environments that would kill most life. Some extremophiles live in boiling water around hydrothermal vents in the ocean. Some live in highly acidic or alkaline environments. Some live in extremely high pressure. Some live in intense radiation. And some live in extreme cold. In Antarctica, scientists have found microorganisms living in ice at temperatures below minus 30 degrees Celsius. These psychrophilic bacteria have adapted proteins that remain flexible in cold temperatures. On Earth, the coldest consistently inhabited environment is probably the interior of Antarctica, where temperatures stay below minus 50 degrees Celsius year-round. Tardigrades, also known as water bears, are microscopic animals that can survive extreme conditions, including extreme cold. In laboratory experiments, tardigrades have survived being cooled to 0.3 Kelvin, just a fraction of a degree above absolute zero. How do they survive? They enter a state called cryptobiosis, where they lose almost all their water. Their metabolism shuts down, and they essentially become dormant. In this state, they can survive being frozen, irradiated, and exposed to vacuum for extended periods. When conditions improve, tardigrades can revive and return to normal function. This suggests that life could potentially survive in the cold of space, at least in a dormant state. If microorganisms were protected from radiation and sealed inside a spacecraft or on an asteroid, they could potentially survive the journey between star systems. This is called panspermia, the idea that life or the seeds of life could travel between worlds through space. While we don't have definitive proof that panspermia has ever occurred, the survival capabilities of extremophils like tardigrades suggest it's possible in principle. Now, let me talk about Mars and its temperature challenges in detail. Mars is cold, very cold. The average temperature on Mars is about minus 65 degrees Celsius, with temperatures ranging from about minus 140 degrees Celsius in winter at the poles to about plus 20 degrees Celsius on summer days in equatorial regions. Why is Mars so cold when it's the second planet from the Sun? Several factors contribute. First, Mars is much farther from the Sun than Earth. It receives only about 43% of the solar energy that Earth does. Second, Mars has a very thin atmosphere. Earth's atmosphere traps heat through the greenhouse effect. Mars's atmosphere is so thin that it provides almost no insulation. Heat radiates away to space much faster on Mars than on Earth. Third, Mars's thin atmosphere also means there's very little convection to distribute heat around the planet. On Earth, the atmosphere circulates heat from the equator to the poles. On Mars, the thin atmosphere can't do this as effectively. The combination of these factors means that Mars is a cold, inhospitable world. For future human missions to Mars, dealing with the cold is one of the major challenges. Spacesuits will need to provide insulation and active heating. Habitats will need to be heated, requiring significant power input. On Mars, solar power is less effective than on Earth due to the thin atmosphere reducing sunlight. Nuclear power or advanced wind-sought geothermal power will likely be necessary. The cold of Mars is a significant obstacle to colonization, but it's not insurmountable. With sufficient power and good engineering, humans can create livable environments on Mars. Let me now talk about the moons of Jupiter and Saturn, which are even colder than Mars. Europa, one of Jupiter's moons, is one of the most interesting worlds in the solar system. It's covered in a thick shell of ice. The surface temperature of Europa is about minus 110 degrees Celsius at the equator and minus 220 degrees Celsius at the poles. But beneath the ice shell, scientists believe there's a liquid water ocean. This ocean is kept warm by tidal heating. The friction generated by Jupiter's gravity pulling on Europa as it orbits. The depth of the ocean is estimated at 100 kilometers or more. The temperature of the water is unknown but is likely well above freezing, perhaps even hot near the ocean floor where hydrothermal vents might exist. Europa's ocean has been in existence for billions of years, providing a stable, warm environment protected by the ice shell from the cold vacuum of space above. This makes Europa one of the most promising places to search for life in the solar system. But exploring Europa means dealing with the extreme cold of the surface and the radiation belts of Jupiter. Enceladus, one of Saturn's moons, is another interesting world. Like Europa, it has a subsurface ocean beneath an icy shell. The surface of Enceladus is even colder than Europa's, with temperatures around minus 200 degrees Celsius. Enceladus also has geysers, plumes of water and organic material erupting from the surface into space. These geysers are believed to originate from the subsurface ocean and provide a way to sample the ocean's contents without drilling through the ice. Titan, the largest moon of Saturn, is another fascinating world. It's the only moon in the solar system with a thick atmosphere. Titan's surface temperature is minus 179 degrees Celsius. At this temperature, water is as hard as rock. Instead, Titan has lakes and seas of liquid methane and ethane. The atmosphere of Titan is thicker than Earth's and consists primarily of nitrogen with some methane. The methane creates a greenhouse effect, keeping Titan warmer than it would otherwise be. Titan is one of the few places in the solar system where organic chemistry is happening on a planetary scale. Complex organic molecules are forming in the atmosphere and accumulating on the surface. If life exists on Titan, it would need to use entirely different chemistry than Earth life. Instead of water, it might use liquid methane as a solvent. Instead of carbon-based biochemistry, it might use silicon-based chemistry or other exotic possibilities. Exploring these cold worlds will be one of humanity's great challenges in the coming centuries. Now let me talk about the future evolution of the universe and what the cold of space means. If the universe continues to expand forever, and current evidence suggests it will, then the universe will continue to cool. The cosmic microwave background temperature will decrease as the universe expands. In billions of years, the CMB will be even colder than it is today. Stars will eventually burn out. The last stars will stop fusing hydrogen. The last red dwarfs, which can burn for trillions of years, will eventually run out of fuel. After trillions of years, the universe will be essentially empty. The only remnants will be cold, dead objects like neutron stars, black holes, and the ultra-faint ashes of dead stars. This state is called heat death, the ultimate fate of the universe if it continues to expand forever. In heat death, the universe reaches maximum entropy. No work can be done. No energy can flow from one place to another. The universe is dead. How far away is heat? Death? Cosmologists estimate that if the current expansion continues, heat death might occur in about 10 to the power of 100 years, a number so large that it's almost incomprehensible. To put this in perspective, the current age of the universe is only about 10 to the power of 10 years. Heat death is 10 to the power of 90 times further in the future. The cold of space is thus the ultimate fate of the universe. Not a quick death, but a slow, gradual cooling over incomprehensible timescales. This is a sobering thought. The universe as we know it, with stars, galaxies, and the possibility of life, is temporary. Yet within this vast, cold universe, we exist. We've evolved on a warm planet orbiting an average star. We've developed consciousness and the ability to understand the universe. We look out at the cold of space and wonder. We're motivated to explore it, to understand it, to reach into it. The cold is indifferent to our ambitions. But we persist nonetheless. Let me discuss the engineering of spacesuits in much greater detail because it's one of the most complex engineering challenges in history. A modern spacesuit is an incredibly complex piece of equipment. It has to provide pressure to keep the astronaut's body from exploding in the vacuum. It has to provide oxygen to breathe. It has to remove carbon dioxide. It has to regulate temperature. It has to protect against radiation and micrometeorite impacts. It has to provide mobility so the astronaut can work. It has to have communications equipment. It has to have emergency life support. The modern EVA suit used on the International Space Station is called the Extravehicular Mobility Unit, EMU. It weighs about 280 pounds on Earth, though in microgravity, it weighs nothing but still has mass and inertia. The suit has multiple layers. The outermost layer is a micrometeorite protection layer made of tough nylon. Below that is an insulation layer. Below that is the pressure bladder, which maintains the suit pressure. Below that are circulation loops for the liquid cooling garment. The liquid cooling garment is essentially underwear with tubing running through it. Water circulates through these tubes, absorbing heat from the astronaut's body. The water flows from the suit through a hose back to the primary life support subsystem, where it passes through a radiator. The radiator in the primary life support subsystem is where the heat is actually radiated away into space. This is the critical component for thermal control. The suit also has a helmet which is transparent to allow the astronaut to see. The helmet has a protective visor that protects the transparent visor from impacts and radiation. The helmet has a head-mounted display showing data to the astronaut. The suit also has a backpack called the Primary Life Support Subsystem, PLSS, which contains the oxygen supply, carbon dioxide removal system, water supply for cooling, and the radiator. Modern suits use about 8 pounds of oxygen per EVA. The carbon dioxide is removed by passing the exhaled air through a carbon dioxide scrubber containing lithium hydroxide in older suits or other carbon dioxide removal chemicals. The suit is designed to maintain a pressure of about 4.3 psy, which is much lower than Earth's atmospheric pressure of 14.7 psy. This lower pressure reduces the risk of the suit becoming too stiff to move in, but it requires special procedures. Astronauts have to do a pre-breathe protocol before a spacewalk, breathing pure oxygen to purge their bodies of nitrogen to reduce the risk of the bends, decompression sickness. One of the most challenging aspects of suit design is maintaining temperature. An astronaut doing physical work might generate 200 watts or more of heat. The suit's radiator has to be able to dissipate this much heat into space. The area of the radiator is limited by the size of the suit. Too small a radiator and the suit will overheat. Too large a radiator and the suit becomes bulky and hard to work in. Modern suits use about 1.5 square meters of radiator area, which can dissipate a few hundred watts of heat. The effectiveness of the radiator depends on the temperature difference between the radiator and space. The warmer the radiator is, the more heat it radiates. The colder space is, the more heat the radiator can emit. For future spacesuits designed for the Moon or Mars, thermal control will be even more critical. On the Moon, in the shadow of a crater, temperatures drop to minus 170 degrees Celsius. A radiator can be very effective in these conditions, but on the sunlit side of the Moon, temperatures reach 120 degrees Celsius, and radiators must work harder to shed heat. For Mars, the challenge is different. Mars has an atmosphere, so convection is possible. Heat can be transferred through the atmosphere, but Mars is so cold that even with this, maintaining a comfortable temperature inside a spacesuit is challenging. Now let me talk about the physics of radiation in detail, because it's the fundamental mechanism by which heat is transferred in space. All objects emit electromagnetic radiation. The hotter an object is, the more radiation it emits, and the shorter the wavelength of that radiation. The relationship between temperature and radiation is described by the Stefan-Boltzmann law, which states that the power radiated by an object is proportional to the fourth power of its temperature. P equals epsilon sigma A T to the power of 4, where P is the power radiated, epsilon is the emissivity, how well the object radiates, sigma is the Stefan-Boltzmann constant, A is the surface area, and T is the absolute temperature. This T to the power of 4 dependence is crucial It means that doubling the temperature results in 16 times more radiation. The wavelength of the radiation emitted is described by Wien's displacement law. Lambda max equals B over T, where lambda max is the peak wavelength, B is Wien's constant, and T is the temperature. At room temperature, about 300 Kelvin, this gives a peak wavelength of about 10 micrometers, which is in the infrared region. At the temperature of the cosmic microwave background, 2.7 Kelvin, the peak wavelength is about 1 millimeter, which is in the microwave region. At higher temperatures, like the surface of the Sun, 5,800 Kelvin, the peak wavelength is about 500 nanometers, which is in the visible region of the spectrum. These laws have profound implications. An object at room temperature radiates primarily in the infrared. This is why thermal imaging cameras can see room temperature objects by detecting their infrared radiation. An object at the temperature of the cosmic microwave background radiates primarily in the microwave region, which is why satellites like COBE, WMAP, and Planck had to observe in microwave wavelengths to detect the cosmic microwave background. The Stefan Boltzmann law also explains why cooling systems in spacecraft can be effective. A small increase in radiator temperature results in a much larger increase in radiated power. By having the radiator at a temperature just above the surroundings, it can effectively radiate heat. In space, where the surroundings are 2.7 Kelvin, an object at 300 Kelvin radiates far more than it receives back. The net heat loss is very rapid. Now let me talk about the scientific experiments that have been done to study the cosmic microwave background and confirm our understanding of the universe. The cosmic microwave background was accidentally discovered in 1964, but scientists quickly realized its importance. Measurements of the CMB could test predictions of Big Bang cosmology and tell us about the universe's composition and geometry. The COBE satellite, launched in 1989, was the first dedicated mission to measure the CMB. COBE had several instruments. The differential microwave radiometer, DMR, measured the temperature of the CMB across the sky. It found that the CMB is incredibly uniform. The temperature is about 2.72548 Kelvin in all directions. But it also found tiny variations, tiny ripples in the temperature at the level of 1 part in 100,000. These tiny variations are crucial. They represent the seeds of the structure in the universe. The slightly warmer regions in the early universe had slightly higher density. Gravity amplified these differences, causing them to grow into the galaxies and clusters we see today. The WMAP satellite, launched in 2001, had higher resolution than COBE. It could measure the temperature variations in greater detail. WMAP's maps of the CMB became iconic images in cosmology, showing the patterns of temperature variations across the entire sky. From WMAP's measurements, scientists could determine key properties of the universe. The age of the universe, 13.7 billion years. The composition of the universe, 5% ordinary matter, 27% dark matter, 68% dark energy. The geometry of the universe, flat, consistent with the Big Bang prediction. The expansion rate of the universe, known as the Hubble constant, the Planck satellite, launched in 2009, had even higher resolution than WMAP. Planck measured the CMB temperature variations with unprecedented precision. Planck confirmed WMAP's measurements and refined them. The age of the universe, 13.82 billion years. The composition and expansion rate were measured with even higher precision. These measurements have revolutionized cosmology. We now have a precise, detailed picture of the universe's geometry, composition, and history. All of this information comes from measuring the temperature of the cosmic microwave background. The cold of space is thus not just an environmental fact, it's a source of profound knowledge about the universe itself. Let me now discuss the history of understanding temperature and cold, because it's a fascinating story of scientific progress. For most of human history, temperature was understood only qualitatively. Something was hot or cold, and that was the extent of the knowledge. In the 1600s, scientists began inventing thermometers. Galileo designed a device that used the expansion of air to measure temperature, though it wasn't very practical. Robert Boyle discovered that gases change volume in proportion to their temperature. This led to the development of gas thermometers, which are still used today for precise temperature measurement. In 1701, Ole Christensen Rømer proposed a temperature scale based on two reference points: the freezing point of water, which he set to 0, and the boiling point of water, which he set to 60. This was essentially the first proper temperature scale. In 1742, Anders Celsius proposed a similar scale, but with the values reversed: 100 for freezing and 0 for boiling. Eventually, this was corrected to what we use today: 0 for freezing and 100 for boiling. But the fundamental question remained: what is the actual minimum temperature? Is there a lowest temperature below which you can't go? In the late 1700s, Guillaume Amontons performed experiments with gas thermometers. He noticed that as the temperature decreased, the pressure of the gas decreased. He extrapolated his data and predicted that at a temperature of about minus 240 degrees Celsius, the pressure would reach 0. This was a remarkable insight. Based on the behavior of gases, Amontons had predicted the existence of absolute 0, though his estimate was off by about 33 degrees. In 1848, Lord Kelvin, William Thomson, developed an absolute temperature scale, with 0 Kelvin at what was theoretically the lowest possible temperature. He calculated this to be at about minus 273.15 degrees Celsius, based on the gas laws. For the next century, the challenge was to actually achieve these low temperatures. In 1877, Raoul Pictet and Louis Cailletet independently liquefied nitrogen, reaching temperatures of about 77 Kelvin. In 1895, James Dewar liquefied hydrogen, reaching about 20 Kelvin. In 1908, Heike Kamerlingh Onnes liquefied helium, reaching about 4 Kelvin. This was close to the temperature of the cosmic microwave background. Kamerlingh Onnes's work on liquefied helium led to discoveries that changed physics. He found that at very low temperatures, some metals lost all electrical resistance, becoming superconductors. He found that liquid helium below 2.2 Kelvin became a superfluid, flowing without viscosity. These discoveries opened up the field of low-temperature physics, which continues to be active today. But even as scientists developed technology to cool materials to nearly absolute 0, they didn't realize that space itself was naturally even colder, at least in terms of the radiation field, which is at 2.7 Kelvin. The discovery of the cosmic microwave background was thus a humbling moment for physics. The entire universe was naturally colder than the coldest temperatures physicists had managed to achieve in laboratories. It also showed that space is not empty. Space is filled with radiation. Space has properties. Space has a temperature. This realization changed our understanding of the universe fundamentally. Now, let me reflect on what all of this means for our understanding of the universe and our place in it. Space is cold. This is one of the most fundamental facts about the universe. The vacuum of space has a temperature of 2.7 Kelvin, corresponding to radiation from the Big Bang, redshifted by billions of years of cosmic expansion. This cold is not just a physical phenomenon, it's a window into the past. By studying the cosmic microwave background, we're studying the universe when it was only 380,000 years old. The cold is also a window into the future. The universe continues to cool as it expands. In the distant future, after trillions of years, the universe will be even colder, approaching heat death. The cold reminds us that we live in a brief, warm moment in the history of the universe. The stars that provide light and warmth are temporary. The habitable worlds will eventually become cold and barren. Yet within this cold universe, life has emerged. We are warm creatures in a cold cosmos. We generate heat through metabolism. We build shelters to protect ourselves from the cold. We have technology to explore the cold. In space, we've learned to live in the cold, albeit briefly and with great effort. We've sent machines to explore worlds far colder than any place on Earth. We've detected the very radiation that fills the universe with cold. Let me explore some fascinating topics related to the cold of space that I haven't fully covered yet. First, let's talk about exoplanets and their temperatures. We've discovered thousands of planets orbiting other stars. Some are hot, some are cold, and understanding their temperatures tells us about their potential habitability. Hot Jupiters are gas giant planets in close orbits around their stars. These planets can reach surface temperatures of thousands of degrees Kelvin. They're certainly not habitable, but some exoplanets orbit in the habitable zone, the region around a star where liquid water could exist. These potentially habitable exoplanets have equilibrium temperatures somewhere around 250 to 350 Kelvin, depending on their distance from their star and the star's luminosity. However, actually measuring the temperature of exoplanets is extremely difficult. We can't point a telescope at them and read a thermometer. Instead, we observe their thermal radiation or the way they pass in front of their stars. When an exoplanet passes in front of its star, from our perspective, some of the star's light passes through the planet's atmosphere. By analyzing the light that makes it through, we can determine what gases are in the atmosphere and sometimes estimate the temperature. Some exoplanets orbit very close to their stars and are extremely hot. Others orbit far from their stars and are extremely cold. A few orbit in the habitable zone and might have moderate temperatures suitable for life. The coldest exoplanets are those orbiting far from dim stars. These could have temperatures far below what we'd consider habitable. Now let me talk about black holes and their temperature, which is a fascinating consequence of quantum mechanics. Black holes are often thought of as infinitely hot, infinitely dense objects. But Stephen Hawking discovered in 1974 that black holes actually have a temperature and can emit radiation. According to Hawking's calculations, a black hole has a temperature inversely proportional to its mass. A stellar mass black hole, formed from a collapsed star, might have a temperature of a few millionths of a Kelvin. A supermassive black hole at the center of a galaxy might have a temperature far lower, approaching absolute zero. But according to Hawking radiation, black holes slowly evaporate, emitting radiation. As they evaporate, they get smaller, their temperature increases, and they emit radiation faster. Eventually, a black hole will evaporate completely in a burst of radiation. This is a profound result. It means that even black holes, the most extreme objects in the universe, have a temperature and obey the laws of thermodynamics. Let me talk about the interstellar medium, the gas and dust between stars. The interstellar medium is not uniform. There are dense clouds and tenuous regions. The temperature varies from very cold to quite warm. In the densest clouds, where molecules dominate and dust shields the interior from starlight, temperatures can be just a few degrees above absolute zero. In regions exposed to starlight or cosmic rays, temperatures are higher, perhaps tens or hundreds of Kelvin. In regions near hot stars, temperatures can reach thousands of Kelvin. The interstellar medium is where new stars are born. Dense clouds of gas and dust collapse under gravity, forming protostars, which heat up as they collapse until eventually reaching temperatures high enough for nuclear fusion to begin. The temperature of the interstellar medium thus plays a crucial role in star formation and the evolution of galaxies. Now, let me talk about biological antifreeze and the adaptations of organisms to extreme cold. Many organisms that live in cold environments have evolved specialized proteins called antifreeze proteins or cryoprotectants. These proteins work by adsorbing to the surface of ice crystals and preventing them from growing larger. This lowers the freezing point of the fluid inside the organism's cells. Fish in Antarctic waters have antifreeze proteins that allow them to survive in water well below the normal freezing point of water. Tardigrades, as I mentioned earlier, can lose most of their water content, reducing the amount of ice that can form in their cells. Some plants produce sugars that lower the freezing point of their sap. This allows them to survive freezing temperatures. Some insects produce glycerol, a natural antifreeze that lowers the freezing point of their body fluids. These adaptations show that life is remarkably resourceful at surviving in cold environments. While space at 2.7 Kelvin is beyond what any known Earth organism can survive, the adaptations we see in Earth's extremophiles suggest that life itself isn't fundamentally limited to a narrow temperature range. Let me discuss the thermodynamic arrow of time, the concept that time flows in one direction because entropy increases. The second law of thermodynamics states that entropy always increases in a closed system. This means that disorder always increases. Order becomes disorder. Hot things cool down, but cold things don't spontaneously become hot. This gives time a direction. We can tell the past from the future because entropy was lower in the past and is higher in the future. The cosmic microwave background is a manifestation of this. The universe was born in a low entropy state. Everything was concentrated in a tiny hot region. As the universe expanded, entropy increased. The radiation was spread out and redshifted. Entropy increased dramatically. The cosmic microwave background represents the current state of very high entropy. In the future, entropy will continue to increase. This thermodynamic arrow of time is one of the deepest concepts in physics. It connects the cold of space to the very structure of time itself. Let me talk about thermal equilibrium and why space reaches a temperature of 2.7 Kelvin. In thermal equilibrium, no net heat flows between objects. All objects are at the same temperature, exchanging radiation equally. In the early universe, everything was in thermal equilibrium at a very high temperature. As the universe expanded, it cooled, but it remained in thermal equilibrium. Even today, the cosmic microwave background represents a kind of thermal equilibrium. The radiation filling space is at a uniform temperature of 2.7 Kelvin. This equilibrium temperature is determined by the expansion history of the universe. As the universe has expanded, the radiation has been red-shifted, lowering its temperature. If the universe continues to expand forever, it will continue to cool. Eventually, in the far future, the temperature will approach absolute zero, though it will never actually reach it. Now, let me discuss the concept of emissivity and how different materials emit radiation at different rates. Emissivity is a measure of how well a material emits radiation compared to an ideal black body, which has emissivity of 1. Shiny metals have low emissivity. They reflect radiation and don't emit much. This is why aluminum foil can be used to reflect heat. Black surfaces have high emissivity. They emit and absorb radiation efficiently. This is why dark objects heat up faster in the sun and cool down faster at night. For spacecraft, thermal control involves choosing materials with appropriate emissivity. Radiators are painted black or specially treated to have high emissivity in infrared wavelengths. Other surfaces are painted white or treated to have low emissivity to reduce heat loss. The International Space Station has distinctive gold-colored insulation. This isn't purely for aesthetics. The gold is a thin layer of an insulating material that has specific thermal properties. Thermal control is thus a careful balance of selecting materials and surface treatments to manage heat flow. Let me talk about the concept of thermal mass and how it affects cooling. Thermal mass is the ability of a material to store heat. Materials with high heat capacity can store a lot of heat without changing temperature much. Water has a very high heat capacity. It takes a lot of energy to change the temperature of water. Metals have lower heat capacity, but they conduct heat efficiently. For spacecraft, thermal mass can be used to buffer temperature changes. If a spacecraft is in sunlight and then goes into shadow, a material with high thermal mass will cool more slowly than a material with low thermal mass. In habitats on the Moon or Mars, thermal mass could be used to help moderate temperature swings. Let me discuss the possibility of life in the clouds of Venus, which is an interesting topic related to temperature. Venus is often described as a hellish world, with surface temperatures hot enough to melt lead. But high in Venus's atmosphere, where the pressure is similar to Earth's sea level pressure, the temperature is actually quite mild, around 0 to 60 degrees Celsius. Some scientists have speculated that microbial life could exist in the clouds of Venus, where the temperature is habitable. However, Venus's clouds are made of sulfuric acid, not water, which makes life, as we know it, very challenging. Still, the existence of habitable temperature zones in Venus's atmosphere reminds us that temperature is just one of many factors determining habitability. Let me talk about future spacecraft and space habitats and how they might manage extreme temperatures. For future Mars bases, thermal control will be critical. One approach is to use passive thermal control, relying on insulation and choosing optimal surface materials. Another approach is active thermal control, using heaters or refrigeration systems to maintain temperature. This requires significant power input. For the Moon, the extreme temperature swings might actually be beneficial for power generation. A thermal gradient between a hot surface and a cold space radiator could be used to generate power, similar to a heat engine. For deep space missions beyond the orbit of Mars, solar power becomes impractical. Spacecraft would need to rely on nuclear power or advanced propulsion systems. For these distant missions, managing the extreme cold becomes a major challenge. Fuel and other liquids can freeze. Electronics can malfunction in extreme cold. Future technology might involve using the cold itself. Cryogenic propellants could be used for propulsion. Cryogenic technology could be used for energy storage. Let me reflect on what it means to be warm in a cold universe. Humans are warm-blooded creatures. Our body temperature is maintained at about 37 degrees Celsius through metabolism. We generate heat by burning food. We can only survive in a narrow temperature range. Deviations of more than a few degrees from normal body temperature cause serious problems. More than 10 degrees and we die. Yet we've built technology that allows us to venture into the cold of space, into environments far colder than any place on Earth. This speaks to human ingenuity and determination. We've understood the physics of heat transfer. We've designed systems to manage temperature in extreme environments. In a sense, we're extending human habitat into places where humans could never naturally exist. The cold of space reminds us that life is fragile. It depends on a narrow range of conditions. It depends on energy from the sun. It depends on the warmth that stars provide. The cold also reminds us that we're temporary. The stars will burn out. The universe will cool. Life as we know it will eventually become impossible. Yet within this vast, cold cosmos, we've emerged. We're conscious beings capable of understanding the universe. We're the universe understanding itself. We're warm pockets of complexity in a cold, simple universe. The cold is indifferent to our existence, but we persist nonetheless. We explore it. We study it. We marvel at it. The cold of space is one of the most profound features of the universe. Understanding it helps us understand everything, from the physics of heat transfer to the history of the universe to our own place in the cosmos. But something to understand and explore. But something to understand and explore. Now let me talk about the future of space exploration and how understanding the cold affects our plans. As humans venture further into space, to Mars, to the moons of Jupiter and Saturn, to the outer solar system, they'll be dealing with colder and colder environments. Mars is cold. Temperatures average around minus 65 degrees Celsius, with extremes dropping to minus 150 degrees Celsius in winter at the poles. The outer planets and their moons are even colder. Jupiter's moon Europa is believed to be about minus 110 degrees Celsius on average. Saturn's moon Titan, which has a thick atmosphere, is minus 179 degrees Celsius. Exploring these worlds will require technology that can function in these extreme temperatures. The good news is that we've already proven we can do this. The Rosetta spacecraft flew past icy objects in space. The New Horizons spacecraft flew past Pluto, where temperatures are about minus 230 degrees Celsius. But sending humans to these places will be more challenging. They'll need spacesuits that can handle the extreme cold. They'll need habitats that can maintain livable temperatures. They'll need energy sources, probably nuclear power or advanced solar systems, to generate the heat they need. One advantage of extreme cold is that cooling becomes easier. Once you're generating heat, getting rid of excess heat is trivial. Just radiate it into the cold environment. This is actually better than on Mars or Earth, where you have to work to cool systems down. Another advantage is that extreme cold can slow down degradation of materials. Some materials, like certain plastics and metals, become brittle in extreme cold, but others become more durable. The challenge is providing heat where needed to keep humans, habitats, and equipment functional. This brings me to a broader point about living in space. The cold is just one of many challenges. There's also radiation, the lack of atmosphere, the lack of gravity, the vast distances between worlds. But the fundamental point is that all of these challenges are solvable with technology. They're not violations of physics, they're engineering problems. Humans have overcome enormous environmental challenges. We've built cities in deserts, in mountains, even underwater. We've crossed oceans. We've walked on the moon. The cold of space is daunting, but it's not insurmountable. Now, let me reflect on what the cold of space tells us about the universe and our place in it. The fact that space has a temperature of 2.7 Kelvin is one of the most profound facts about the universe. It means that the entire universe is filled with radiation from the Big Bang. It means that the universe is still cooling down from its hot beginning. It means that time is asymmetric. Entropy is increasing. The universe had a past, a hot, dense beginning, and it has a future, a cold, dilute end. In the extremely distant future, if the universe continues to expand forever, it will cool even further. Eventually, it might reach a state called heat death, where all energy has been evenly distributed and no further change can occur. The cold of space is a reminder that the universe is vast and ancient. It's a reminder that we're living in a brief, warm moment in the universe's lifetime. The stars are islands of warmth in an ocean of cold. The sun is warming our little planet, allowing life to flourish. But eventually the sun will run out of fuel. Eventually even the sun will cool. The cold of space is inexorable. It's the default state of the universe. Everything eventually gets cold. And yet we persist. We've built spacecraft and spacesuits to explore the cold. We've learned to live, however briefly, in the most extreme environment we know. This speaks to something fundamental about human nature: our curiosity, our drive to understand, our refusal to accept limits. The cold of space is no longer an abstract concept. It's a place we've been, where we've conducted experiments, where we've stood and looked down at Earth. And as we look forward, the cold of space will become more familiar. Human missions to Mars will send people to a cold desert world. Future missions to the moons of Jupiter and Saturn will take us to even colder places. We're learning to live in the cold. We're learning to work with it, to use it, to not just survive in it, but to thrive. The cold of space is one of the defining characteristics of the universe. Understanding it, truly grasping what it means, is part of understanding our place in the cosmos. Space is cold, devastatingly cold, incomprehensibly cold, and we're learning to love it. The journey of a photon from the Big Bang to today is a story that encapsulates the entire history of the universe and the cold that fills it. When the universe was born, at the moment of the Big Bang, the first photons were created in an incredibly hot, dense environment. These photons had enormous energy, corresponding to temperatures of billions of degrees. For the first 380,000 years of the universe's existence, these photons were constantly being absorbed and re-emitted by the plasma of electrons, protons, and neutrons that filled space. Then, something remarkable happened. The universe had expanded and cooled enough that electrons could combine with protons to form hydrogen atoms. This process is called recombination. Once neutral atoms formed, photons could travel freely without being constantly absorbed. The universe became transparent. The photons that were free to travel at this moment are the same photons we detect today as the cosmic microwave background. They've been traveling for 13.82 billion years, redshifted by the expansion of the universe. A photon that had tremendous energy at the moment of recombination now has very little energy. Its wavelength has been stretched from the ultraviolet region to the microwave region. This is why the cosmic microwave background is so cold. These are ancient photons, red-shifted by billions of years of cosmic expansion. The journey of this photon is thus a journey through time. Detecting it is like receiving a message from the early universe, telling us about conditions as they were 380,000 years after the Big Bang. Every photon in the cosmic microwave background has a similar story. They all traveled from the hot early universe to the cold present-day universe, carrying with them the imprint of what the universe was like billions of years ago. In a very real sense, the cold of space is not just a current condition, it's a record of history. It's the Big Bang, redshifted and cooled by time and expansion. Now, let me talk about cryogenics and what scientists have learned about materials at extreme temperatures. Cryogenics is the study and use of materials and systems at very low temperatures, typically below 120 Kelvin. The field of cryogenics has led to remarkable discoveries about how materials behave at extreme temperatures. One of the most famous discoveries is superconductivity. Below a certain critical temperature, some materials lose all electrical resistance. A current flowing through a superconductor will continue indefinitely without any energy input. This was discovered by Kamerlingh Onnes in 1911. He found that mercury became a superconductor when cooled below 4.2 Kelvin. Since then, scientists have discovered many superconducting materials. Some become superconducting at temperatures above 77 Kelvin, the boiling point of liquid nitrogen, which is easier and cheaper to achieve than liquid helium cooling. Superconductivity has practical applications. Superconducting magnets are used in MRI machines and in particle accelerators like the Large Hadron Collider. The theoretical understanding of superconductivity came from a theory called BCS theory, Bardeen-Cooper-Schrieffer, which explained superconductivity in terms of quantum mechanics and the formation of electron pairs. Another remarkable phenomenon discovered at low temperatures is superfluidity. At temperatures below 2.2 Kelvin, liquid helium becomes a superfluid with zero viscosity. A superfluid can flow without friction. It will climb the walls of a container and flow out. It exhibits unusual properties like the ability to conduct heat extremely efficiently. Superfluidity remains an active area of research. It reveals deep truths about quantum mechanics and the nature of matter at extremely low temperatures. Scientists have also discovered that at extremely low temperatures, materials exhibit quantum effects that are normally hidden by thermal motion. At room temperature, atoms are jiggling around due to thermal energy, masking quantum effects. But at very low temperatures, where thermal energy is minimal, quantum effects dominate. Researchers have created Bose-Einstein condensates, states of matter where atoms have such low thermal energy that they enter a quantum ground state and behave collectively as a single quantum entity. This was first achieved experimentally in 1995 and has been studied extensively since. Bose-Einstein condensates reveal the quantum nature of matter. All of these discoveries, superconductivity, superfluidity, Bose-Einstein condensates, are only possible at the extreme, temperatures that space provides or that scientists can achieve in the laboratory. They reveal that the cold isn't just an absence of heat. It's a gateway to exotic physics, to phenomena that defy everyday intuition. Now let me talk about the search for life in extreme environments on Earth and what it tells us about the possibility of life in space. Scientists have found that life on Earth is far more resilient and adaptable than previously thought. In the deepest oceans, miles below the surface, where pressure is extreme and no sunlight penetrates, life exists around hydrothermal vents. Bacteria around these vents don't use sunlight for energy. Instead, they use chemical energy from minerals dissolved in the vent water. In underground aquifers hundreds of meters below the surface, life exists without any connection to the surface world, living off chemical energy and radioactive decay. In ice cores drilled from Antarctica, scientists have found living microorganisms that have been frozen for hundreds of thousands of years. When thawed, some can revive. In the driest parts of the Atacama Desert, where it hasn't rained for decades, life persists in the pore spaces of rocks. In boiling hot springs, bacteria thrive at temperatures up to about 130 degrees Celsius. These discoveries suggest that life is incredibly adaptable. It can exist in environments that we would have thought impossible for life. This has implications for the search for life in space. If life can exist in such extreme environments on Earth, perhaps it could exist in extreme environments in space. Perhaps life could survive in the subsurface oceans of icy moons, shielded from radiation and cold by a layer of ice. Perhaps life could exist in the atmosphere of Venus, where the temperature is mild, though the chemistry is harsh. Perhaps in some form we haven't imagined, life could exist even in the cold of interstellar space. The discovery of extremophils has expanded our conception of where life can exist. Now let me discuss the economic aspects of space exploration and how cold affects the costs. Space exploration is expensive. Developing spacecraft, launch systems, spacesuits, and habitats requires enormous investment. The cost of cooling and thermal management is a significant part of this expense. Radiators add mass to spacecraft. Cooling systems require power and maintenance. For future missions to Mars or the moons of Jupiter and Saturn, thermal management will be a major cost factor. However, there are potential economic benefits to space exploration. Mining asteroids and other celestial bodies could provide valuable resources. Manufacturing in space could produce products impossible to make on Earth. The cold of space could actually be an advantage. Materials can be refrigerated at no cost. Certain processes that require extreme cold could be done in space more efficiently than on Earth. Some researchers have proposed using the cold of space for data center cooling. Theoretically, high-performance servers could be placed in orbit, where the cold vacuum could cool them efficiently. This is speculative technology, but it shows how the properties of space, including its cold, might be exploited for economic benefit. Let me talk about the philosophical implications of the cold of space and what it means for humanity. The cold of space is indifferent. It doesn't care about our existence. It follows the laws of physics, inexorable and unchanging. In the face of this indifference, humanity persists. We explore, we understand, we build. The cold reminds us that the universe operates according to principles beyond our control. We can't change the temperature of space. We can't change the expansion of the universe. We can't change the inevitable cooling of all things. Yet we can understand these principles. We can adapt to them. We can work within them. This is a profound realization. We are not masters of the universe. We are part of it, subject to its laws. But we are conscious parts. We are the universe understanding itself. We are matter that has organized itself in such a way that it can contemplate the cosmos. The cold of space is a reminder of our smallness. We are tiny, temporary creatures in a vast, ancient universe. But it's also a reminder of our capability. We figured out how to survive in the cold. We've built machines to explore it. We've mapped its properties with precision. The cold unites us. All humans share this planet, which is warm and habitable because of our distance from the sun and the composition of our atmosphere. The cold of space is what we're protecting ourselves from. Understanding the cold, understanding the physics of temperature and radiation is part of understanding what makes life on Earth possible. The cold reminds us to appreciate the warmth we enjoy, the habitability of our world, the fragile bubble of livable space we inhabit. It reminds us that what we have is precious and temporary. It also reminds us that the future of humanity might be written in the cold of space. If we're to survive for millions or billions of years, we'll need to learn to live in the cold. We'll need to adapt to other worlds. We'll need to master the physics of thermal control and survival in extreme environments. The cold of space is thus not just a challenge, it's an opportunity. It's where humanity might go next. The cold of space is indifferent, vast, and unforgiving. And yet, we persist. We look toward the stars. We design spacecraft. We train astronauts. We build technology to survive in the cold. We are warm creatures in a cold universe. Let me add one more dimension to this exploration: the personal experience of cold and how it relates to our understanding of space. Every human has experienced cold: the bite of winter wind, the shock of jumping into cold water, the persistent chill of being outdoors in freezing temperatures. Cold is a sensation that humans have millions of years of evolutionary history with. Our ancestors adapted to ice ages. They developed ways to maintain body heat. They learned to seek warmth. But the cold of a winter day in Minnesota, even at minus 40 degrees Celsius, is not truly cold compared to the cold of space. Space is not just cold. It's the absence of heat. It's the default state of the universe. An astronaut in a spacesuit floating in space isn't just cold. They're surrounded by a vacuum that's trying to pull heat away from them with relentless efficiency. Humans evolved to experience cold as discomfort, as a signal that we need to seek shelter and warmth. The cold of space is beyond that sensation. To understand the cold of space, we have to transcend our sensory experience and use our intellectual understanding of physics. We have to understand that the cosmic microwave background radiation filling space has a wavelength of about 1 millimeter, a wavelength we can't see or feel directly, but that we can measure with instruments and understand through physics. We have to understand that heat transfer through radiation is governed by the fourth power of temperature, a mathematical relationship that has profound implications. We have to understand that entropy increases and therefore time flows in one direction, from order to disorder, from hot to cold. These intellectual understandings allow us to grasp something our senses could never grasp directly. They allow us to appreciate that we live in a warm bubble in a cold universe, and that this warm bubble is temporary, and that one day it will cool as well. Now, let me discuss the role of the James Webb Space Telescope in studying cold objects and structures in the universe. The James Webb Space Telescope, launched in 2021, is revolutionizing our understanding of the cold universe. JWST observes primarily in infrared wavelengths. This is perfect for studying cold objects, which emit primarily in the infrared. JWST has studied the cosmic microwave background in detail, refining our measurements of its properties. JWST has observed the most distant galaxies in the universe, revealing what galaxies looked like when the universe was very young. JWST has also studied protoplanetary disks, the regions of dust and gas around young stars where planets are forming. These regions are relatively cold, and infrared observations are ideal for studying them. JWST has observed nebulae and regions of star formation, where the temperatures can range from a few tens of Kelvin to hundreds of Kelvin. As infrared technology advances, we'll be able to study even colder, more distant objects in the universe. Future telescopes, like the Extremely Large Telescope, EIELT, being built in Chile, and the 30-meter telescope, TMT, being built in Hawaii, will have even better infrared capabilities. These telescopes will allow us to study the cold of space in unprecedented detail. Let me discuss the concept of thermal imaging and how we can literally see the heat of objects. Thermal imaging cameras detect the infrared radiation emitted by objects. Different objects at different temperatures emit different amounts of infrared radiation. A thermal imaging camera can be used to see people and animals in the dark because of the infrared radiation they emit. This same principle has been used extensively in space exploration. Spacecraft have thermal imaging systems to monitor their own temperature and the temperature of their surroundings. Orbiters around Mars and other planets have thermal imaging instruments that can map the temperature of the surface. Thermal imaging has revealed that the Moon, has temperature variations of hundreds of degrees between the illuminated and shadowed regions. Thermal imaging has also been used to study the thermal properties of asteroids and comets. By understanding the thermal properties of objects, scientists can determine their composition, their history, and their potential for resource extraction. Thermal imaging is thus a powerful tool for exploring the cold of space and understanding the thermal properties of distant objects. Let me talk about the future of human spaceflight and the role of thermal management. NASA's Artemis program aims to return humans to the moon in the coming years and eventually establish a lunar base. The thermal challenges of the lunar surface are significant. Spacesuits must protect against both the extreme cold in shadow and the intense heat of sunlight. Future lunar habitats will need to maintain livable temperatures while the outside surface varies by hundreds of degrees. The proposed architecture for lunar bases includes habitats partially buried under regolith, lunar soil, to provide insulation and protection from radiation. For Mars missions, which will take place in the coming decades, thermal management will be even more critical because of the lower gravity and the distance from Earth. Spacesuits for Mars will need to be more advanced than current spacesuits, providing better insulation and more efficient cooling systems. Mars habitats will need extensive radiators and possibly active heating systems powered by nuclear reactors. The science of thermal control is thus central to the future of human spaceflight. Let me discuss what scientists call the thermal environment of different parts of space and how it varies. The thermal environment of near-Earth orbit is different from the thermal environment of deep space. Near Earth, the sun provides radiation. Reflected radiation from Earth provides some heat. The cosmic microwave background provides a cold background. The balance between these factors determines the equilibrium temperature of objects in near-Earth orbit. As spacecraft travel farther from the sun, the thermal environment changes dramatically. Solar radiation decreases. The temperature drops. By the time a spacecraft reaches the outer solar system near Neptune and Pluto, the thermal environment is brutally cold. A spacecraft traveling to the outer solar system must rely on nuclear power for heat and electricity because solar power is insufficient. The thermal design of deep space probes is thus completely different from the thermal design of Earth-orbiting spacecraft. Deep space probes use radioisotope thermal generators, RTGs, devices that convert the heat from radioactive decay into electricity and heat. This allows the spacecraft to generate its own heat and power independent of the sun. The Voyager spacecraft, now in interstellar space, are still operating after more than 45 years, powered by ACRTGs. The thermal design of Voyager was so efficient that they're still functioning, still sending data back to Earth in the cold of interstellar space. Let me now talk about what we don't understand about the cold of space and what future discoveries might reveal. We've measured the cosmic microwave background with great precision. We know its temperature is 2.72548 Kelvin, but there are still mysteries. We don't fully understand dark matter and dark energy. We don't know if the universe is truly infinite or has boundaries. We don't know if the cosmic microwave background temperature might have subtle variations that could tell us about the topology of the universe. We don't fully understand the physics of the transition from the quantum realm to the classical realm, and this affects our understanding of the very early universe when the CMB photons were being released. Future observations might reveal new insights about the thermal properties of the universe. Let me explore some additional scientific frontiers related to the cold of space that represent the cutting edge of current research. One fascinating area is the study of neutron stars, which are some of the coldest objects in the universe while paradoxically being born in the hottest events. Supernovae. A neutron star is what remains after a massive star explodes as a supernova. The core of the star collapses, and electrons and protons are forced together to form neutrons. A neutron star is incredibly dense. A teaspoon of neutron star material would weigh 1 billion tons. The temperature at the surface might be around 1 million Kelvin, which is incredibly hot by everyday standards, but actually cool compared to the interior. As neutron stars age, they cool through radiation. Eventually, over billions of years, they can cool to temperatures of just millions of Kelvin. Some of the oldest neutron stars are called cold neutron stars or black widow pulsars, and they've cooled to relatively low temperatures. Studying the cooling of neutron stars tells us about the physics of extremely dense matter and the behavior of matter under conditions we can never replicate on Earth. Another frontier is the study of cosmic rays and their interaction with the cold interstellar medium. Cosmic rays are high energy particles, primarily protons, traveling through space at nearly the speed of light. They come from supernovae and other high energy events. As cosmic rays travel through the cold of interstellar space, they interact with the sparse gas and dust. These interactions can produce secondary particles and radiation. Understanding cosmic rays and their effects is crucial for protecting astronauts from radiation and for understanding the ionization of the interstellar medium. Let me talk about the concept of thermochemistry in space, the chemistry that happens in the cold of the interstellar medium. Chemistry is generally thought of as occurring at room temperature or in laboratory conditions, but chemistry happens in the cold of space as well. In giant molecular clouds where gas is cold and dense, complex organic molecules form. We've detected amino acids, sugars, and other organic molecules in space. How does this chemistry happen in the cold? The mechanisms include ion-molecule reactions, which can happen even at very low temperatures. They include reactions on the surfaces of dust grains, where molecules can stick and react. The chemistry of the interstellar medium is thus a vibrant area of research, revealing how complex molecules can form even in the cold, and suggesting that the building blocks of life might be distributed throughout the galaxy. Let me discuss the search for technosignatures, evidence of advanced civilizations in space, and how thermal signatures might be detected. A highly advanced civilization might use enormous amounts of energy, creating thermal signatures that could be detected from Earth. Some scientists have hypothesized that a civilization might harvest energy from their star using a Dyson sphere, a structure that would surround the star and capture its energy. A Dyson sphere would emit thermal radiation in the infrared as it radiates away the waste heat from the civilization's energy use. Searches for Dyson spheres have been conducted using infrared observations, looking for objects with unusual thermal properties that might indicate an artificial structure. So far, no definitive technosignatures have been detected, but the cold of space makes them theoretically detectable if they exist. The search for extraterrestrial intelligence, SETI, thus has a thermal component, looking for unusual thermal signatures that might indicate advanced civilizations. Let me talk about the role of temperature in the formation of planets and planetary systems. Planets form in the cool regions of protoplanetary disks around young stars. The temperature gradient in the disk determines where different types of planets form. Rocky planets form close to the star, where temperatures are high enough that volatile ices melt. Gas giant planets form farther out, where it's cold enough for hydrogen and helium to be captured. The temperature structure of protoplanetary disks is thus a crucial factor in determining the architecture of planetary systems. By studying the thermal properties of protoplanetary disks with infrared observations, astronomers can understand how planetary systems form. Now let me discuss the implications of the second law of thermodynamics for the structure of the universe. The second law of thermodynamics states that entropy always increases. This has profound implications for the universe. In the early universe, just after the Big Bang, entropy was very low. Everything was highly ordered, concentrated in an infinitely dense point. As the universe expanded, entropy increased. matter clumped together under gravity to form galaxies and stars. These structures are locally ordered, low entropy, but they increase the overall entropy of the universe by radiating energy. Eventually, stars will burn out, galaxies will expand, black holes will slowly evaporate through Hawking radiation. The universe will reach a state of maximum entropy, where all usable energy has been exhausted. This is heat death. The cold of space is thus intimately connected to entropy and the arrow of time. The universe gets colder as it ages because entropy increases and energy disperses. Let me talk about the thermal properties of different materials in space and how material science plays a role in space exploration. Different materials have different thermal properties. Some conduct heat efficiently, others insulate. In space, where heat transfer is primarily through radiation, the color and surface properties of materials matter enormously. Black materials absorb and emit radiation efficiently. White materials reflect radiation. Scientists have developed specialized materials for spacecraft that have carefully engineered thermal properties. Multi-layer insulation, MELI, also called space blanket material, consists of many thin layers separated by air gaps. This design minimizes radiative heat transfer. Aerogel is an extremely low-density material with excellent insulating properties. It's been used on Mars rovers. Thermal paints and coatings are engineered to have specific emissivity in infrared wavelengths to maximize or minimize heat transfer. The science of materials at low temperatures has revealed that some materials become brittle in extreme cold. Others actually become stronger. Metals become more brittle. Ceramics can become stronger and more ductile at low temperatures, which is counterintuitive. Understanding these material properties is crucial for designing systems that will work in the cold of space. Let me discuss the future of terraforming and thermal engineering on other worlds. Terraforming, making another planet habitable for humans, would require managing the thermal environment of the entire planet. For Mars, terraforming might involve thickening the atmosphere to increase the greenhouse effect and warm the planet. This could be done by releasing greenhouse gases like CFCs or by using mirrors to concentrate sunlight. As the planet warms, water ice would melt, creating liquid water. The thickened atmosphere and liquid water would create a habitable environment. But all of this depends on thermal engineering at a planetary scale. For Venus, terraforming is even more speculative. The planet would need to be cooled drastically. Some proposals suggest using vast mirrors to shade Venus from the sun. These are long-term projects, probably requiring thousands of years. But they illustrate how thermal management becomes crucial when thinking about planetary engineering. Let me talk about the cosmic perspective that understanding the cold of space gives us. When we understand that space is cold, that the universe is expanding and cooling, that our sun is temporary, we gain a cosmic perspective. We realize that we live in a brief moment of cosmic history when the universe happens to support life. We realize that our planet is a warm oasis in a cold desert. We realize that everything we know and love is temporary. Stars will burn out. Planets will drift into space. Life will eventually disappear from the universe. This might sound depressing, but I think it's actually liberating. It frees us from the illusion that anything is permanent. It encourages us to value what we have now. It encourages us to appreciate the warmth and beauty of our world. It encourages us to preserve life and consciousness while they can exist. It encourages us to explore and understand the universe, not because we can conquer it, but because understanding it is one of the most profound things conscious beings can do. The cold of space, when understood deeply, becomes not a threat, but a teacher. It teaches us about the nature of reality. It teaches us about time and entropy. It teaches us about our place in the cosmos. Let me delve into some specific case studies of thermal management challenges that have faced actual space missions, because these real world examples illustrate the profound complexity of dealing with the cold. The Apollo missions to the moon were some of humanity's greatest achievements in thermal management. The spacesuits had to protect against temperatures ranging from 120 degrees Celsius in sunlight to minus 170 degrees Celsius in shadow, a swing of nearly 300 degrees. The solution involved multiple layers of material, each serving different functions. The outer layer was a protective micrometeorite shield. Below that were layers of insulation. The pressure suit was inside, maintaining internal pressure, and the inner layers included cooling systems. The spacesuits worked remarkably well. Astronauts spent hours walking on the lunar surface, working in this extreme thermal environment, generating metabolic heat that had to be radiated away while being protected from the intense solar radiation. The success of Apollo was thus in large part a success of thermal engineering. Without the sophisticated spacesuit technology, the missions would have been impossible. Another example is the Mars Pathfinder mission and its Sojourner rover. The rover had to operate on Mars, where temperatures dropped below minus 100 degrees Celsius at night. The rover had a small radioisotope heater unit, RHU, powered by plutonium 238, a radioactive isotope. This provided just enough heat to keep the rover's electronics functional through the cold Martian night. The rover also had solar panels for power during the day, but these were much less efficient than on Earth due to Mars's distance from the Sun and the Martian atmosphere. The thermal design of Sojourner was thus a careful balance between active heating for survival and passive insulation to minimize heat loss. More recently, the Curiosity and Perseverance rovers on Mars use larger radioisotope heater units and more sophisticated thermal insulation. Perseverance can operate for years on Mars despite the extreme cold. The success of Mars rovers demonstrates that humans have learned to design systems that can survive and function in the cold of space. Now, let me talk about the physics of planetary atmospheres and how atmosphere affects temperature. An atmosphere traps heat through the greenhouse effect. Greenhouse gases like carbon dioxide, methane, and water vapor absorb infrared radiation that would otherwise escape to space. This is why Venus, despite being closer to the Sun than Mercury, is actually hotter. Venus's thick atmosphere of carbon dioxide creates an extreme greenhouse effect, with surface temperatures reaching 460 degrees Celsius. Mars, on the other hand, has a very thin atmosphere, so the greenhouse effect is minimal. Mars is much colder than Earth despite being in the habitable zone. Earth's atmosphere creates a moderate greenhouse effect, maintaining temperatures suitable for life. The thickness and composition of a planet's atmosphere thus has a huge effect on its temperature. This is relevant to terraforming Mars. By thickening the atmosphere and adding greenhouse gases, you could warm Mars significantly over time. This is also relevant to understanding Venus and why it's so hot despite having an atmosphere. The atmosphere is thus crucial to understanding planetary temperatures. Let me discuss the concept of heat transport in stars and how it affects stellar structure and evolution. Inside a star like the Sun, energy is generated through nuclear fusion in the core. This energy has to be transported outward to the surface, where it's radiated into space. There are different mechanisms for heat transport. In the core, where the temperature is highest and density is highest, radiation is the primary mechanism. Photons carry energy outward. In the outer regions of the sun, where the temperature is lower and density is lower, convection becomes important. Hot material rises, cools, and sinks, creating circulation patterns that transport heat. At the surface of the sun, the photosphere, radiation dominates. The sun radiates its energy into space as photons. The structure and evolution of stars depend critically on how efficiently they can transport heat from the core to the surface. If heat transport is efficient, the star is stable. If it's inefficient, the star can become unstable. This is related to stellar rotation and other properties. It's also related to the age of the star and how long it can maintain fusion. Understanding heat transport in stars is thus central to understanding stellar physics. Let me now talk about the fate of the sun and how it relates to the cold of space. The sun is about 4.6 billion years old. It has about 5 billion years of life remaining before it runs out of hydrogen fuel. As the sun ages, it gets brighter. The brightness increases gradually as the hydrogen in the core is converted to helium. The core becomes slightly smaller and denser, and the hydrogen burning becomes more intense. In about 1 billion years, the sun will be bright enough that the oceans on Earth will evaporate. Earth will become a hot, dry, lifeless world. In about 5 billion years, the sun will run out of hydrogen in its core. It will expand into a red giant, engulfing the inner planets, including Earth. The sun's surface will cool. The outer layers of a red giant are cooler than the sun's current surface, but the core will heat up tremendously. Eventually, the sun will shed its outer layers into space, leaving behind a white dwarf, a small, dense remnant about the size of Earth. This white dwarf will then slowly cool over billions and billions of years, eventually becoming a black dwarf, a dead star, dark and cold. But this won't happen for an enormously long time. The cooling of white dwarfs is so slow that the universe isn't old enough yet for any black dwarfs to have formed. The future of our sun thus involves becoming hot and bright, then dying and cooling. But it won't truly be cold in the cosmic sense for an unimaginably long time. Let me talk about the chemical composition of the universe and how it affects temperature and thermal properties. The universe consists primarily of hydrogen and helium, the two lightest elements. These make up about 98% of ordinary matter. Heavier elements like carbon, oxygen, nitrogen, and iron make up only about 2% of ordinary matter. But these heavier elements are crucial for the thermal properties of matter and for the formation of planets and life. Hydrogen and helium have relatively simple thermal properties. They're gases at most temperatures encountered in space. Heavier elements can form complex compounds with various thermal properties. The composition of a star, planet, or nebula affects its thermal behavior. For example, the composition of planetary atmospheres determines their greenhouse effect and hence their temperature. The composition of stellar interiors affects how heat is transported. Understanding the relationship between composition and thermal properties is thus important for understanding the universe. The study of temperature in the universe extends to some of the most exotic and extreme objects known to physics. White dwarfs are stellar remnants about the size of Earth, but with the mass of the sun. They're incredibly dense. A teaspoon of white dwarf material would weigh millions of tons. A newly formed white dwarf might have a surface temperature of several million Kelvin, but white dwarfs cool very slowly. After tens of billions of years, they might cool to just thousands of Kelvin. Neutron stars, as I mentioned earlier, are formed in supernovae. They're even denser than white dwarfs. Their surface temperatures can be millions of Kelvin, but they also cool slowly. These remnants of dead stars demonstrate the wide range of temperatures in the universe. Let me also discuss the role of temperature in the formation of the first stars in the universe. The first stars formed about 100 million years after the Big Bang from the primordial hydrogen and helium. The temperatures in the cores of these first stars were sufficient for hydrogen fusion to begin. These first stars were probably massive and short-lived, burning out quickly. When they exploded as supernovae, they created heavier elements, carbon, oxygen, silicon, iron, and scattered them into space. These elements became incorporated into subsequent generations of stars and planets. We are thus made of material forged in the cores of ancient stars. Our carbon, our oxygen, our iron all came from stellar nucleosynthesis in the hot cores of stars billions of years ago. The temperature of stellar cores is thus not an abstract fact, but a fact that directly connects to our own existence. Now let me discuss the concept of temperature in quantum systems and how quantum mechanics affects our understanding of temperature. In classical thermodynamics, temperature is simply a measure of average kinetic energy. But in quantum mechanics, things are more subtle. According to quantum mechanics, even at absolute zero, there's residual motion, 0 point energy. You can never have perfect stillness. Additionally, in quantum systems, energy comes in discrete packets called quanta. The spacing between energy levels determines what temperatures are needed for transitions between levels. At very low temperatures, quantum effects dominate. Macroscopic quantum phenomena like superconductivity and superfluidity emerge. At very high temperatures, quantum effects are less important, and classical thermodynamics applies. This connection between temperature and quantum mechanics is one of the deep insights of 20th century physics. Let me talk about the role of temperature in chemical reactions in space. Chemistry happens at all temperatures. Even at the coldest temperatures in space, chemical reactions can occur, though much more slowly than at room temperature. The rate of a chemical reaction depends exponentially on temperature, a what described by the Arrhenius equation. At low temperatures, reactions proceed very slowly. But in the dense regions of molecular clouds, even with low temperatures, reactions can accumulate over time to produce complex molecules. This is particularly important for understanding prebiotic chemistry, the chemistry that led to the origin of life on Earth. Meteorites that fell on Earth brought organic molecules synthesized in the cold of space. These molecules might have contributed to the emergence of life. Temperature thus affects chemical reactions in space and potentially affected the origin of life. Now let me reflect on the relationship between the observer and the observed when it comes to temperature. Temperature is fundamentally about motion and energy at the microscopic level, but we can only observe it macroscopically through its effects. A thermometer measures the expansion of a liquid, which depends on the temperature. A radiometer measures the radiation emitted, which depends on the temperature. In this sense, temperature is something we infer from observations. We never directly observe motion of individual atoms. We infer that space has a temperature of 2.7 Kelvin from observing the cosmic microwave background radiation. We infer that the core of the sun has a temperature of millions of Kelvin from the radiation it emits and the physics of nuclear fusion. This relationship between observation and inference is central to how science works. We build models based on observations, and then we test whether our models correctly predict new observations. Temperature is one of the most fundamental quantities in these models. Let me now talk about the challenge of maintaining accurate temperature measurements in space. Measuring temperature in space is more difficult than it might seem. Instruments are exposed to intense radiation from the sun on one side and the cold of space on the other. Thermometers can be affected by solar radiation, leading to false readings. Scientists have developed techniques to isolate thermometers from solar radiation while allowing them to radiatively couple to the environment they're measuring. They use radiative shields, sunshades, and careful calibration. The precision of temperature measurements in space is crucial for understanding the universe. Errors in temperature measurements lead to errors in understanding stellar properties, planetary atmospheres, and the cosmic microwave background. The cosmic microwave background measurements by Kobe, WMAP, and Planck required extraordinary precision, measuring temperatures to a small fraction of a Kelvin. This precision was achieved through careful instrument design, calibration, and data analysis. The fact that we can measure the temperature of the cosmic microwave background to such precision is a testament to the sophistication of modern technology. Let me discuss the concept of thermal inertia and how it affects planetary temperature. Thermal inertia is a measure of how quickly an object heats up or cools down. Objects with high thermal inertia change temperature slowly. Objects with low thermal inertia change temperature rapidly. On planets, thermal inertia depends on the heat capacity of the surface materials. Sand and dust have low thermal inertia. They heat up quickly during the day and cool down quickly at night. Rock and water have higher thermal inertia. They heat and cool more slowly. This affects the daily temperature variations on planets. Mars, with its dry surface of sand and rock, has large daily temperature variations. The sun side might be warmer while the night side is much colder. The moon has even larger temperature variations because it has almost no atmosphere to distribute heat. The thermal inertia of planetary surfaces thus affects the range of temperatures on those worlds. Understanding this is important for predicting where liquid water might exist and where life might survive. Let me talk about one more frontier in understanding temperature: the role of temperature in the evolution of galaxies. Galaxies form when gas collapses under gravity in the early universe. The collapse heats the gas. The temperature reaches millions of Kelvin in the dense cores. At these temperatures, gravity is balanced by pressure from the hot gas. Stars form in this hot gas. The energy from stellar radiation and supernovae heats the gas further. Eventually, the galaxy reaches a kind of equilibrium where the heat from stars is balanced by the cooling of the gas. The temperature of gas in galaxies thus affects galaxy formation, star formation, and the evolution of galaxies over cosmic time. Understanding the temperature structure of galaxies is a frontier of astrophysics. Finally, let me discuss what the future of physics might reveal about the nature of temperature and cold. Current physics understands temperature through classical thermodynamics and statistical mechanics, but there are mysteries that future physics might solve. For example, we don't fully understand the relationship between entropy and the arrow of time. Why does entropy increase? Is there a deeper principle beneath the second law of thermodynamics? We don't understand dark matter and dark energy, which make up 95% of the universe. These might have thermal properties that we don't yet comprehend. We don't have a complete theory of quantum gravity, which would apply to extreme conditions like the singularity at the center of black holes or the earliest moments of the Big Bang. These extreme regimes have temperatures and densities far beyond what we can currently measure or understand. Future theories of physics might reveal that temperature is not fundamental, but is emergent from deeper principles. Or they might reveal new forms of temperature-like quantities that apply in quantum systems or curved spacetime. The nature of temperature and cold remains an open frontier of physics, even after centuries of study. What we know is that space is cold. We know that this cold has shaped the universe. We know that understanding it requires understanding the deepest principles of physics. What we don't know is what future discoveries might reveal. What new insights might change our understanding? What I do know is that the search for understanding is itself a warm fire in the cold cosmos. It's the light of consciousness trying to understand itself and its universe. Let me add one final thought about the thermal engineering challenges facing humanity's expansion into space. When we think about colonizing Mars or the moons of Jupiter and Saturn, we often focus on the challenges of reaching those worlds, the rocket engineering, the trajectory calculations, the life support systems. But thermal management might be as important as any of these. It's the unglamorous, behind-the-scenes engineering that makes survival possible. Mars habitats will need radiators and heating systems. Spacesuits will need layers of insulation and active cooling. Power systems will need to generate enough electricity not just for computers and life support, but for heating. On Titan, with its methane lakes and nitrogen atmosphere, thermal engineering challenges are even more extreme. On Europa, beneath the ice, the subsurface ocean is warmed by tidal heating, but reaching it requires drilling through the ice, which requires thermal control to prevent the hole from refreezing. These challenges drive innovation. They require engineers to think creatively about materials, systems, and processes. But they also reveal something profound, that the cold of space, which seems like an obstacle, is actually manageable. Humans can understand it. We can work with it. We can use it. The cold is not our enemy. It's a constraint that we've learned to work within. This is ultimately an optimistic message. Yes, space is cold. Yes, it's hostile. But humans have the ingenuity to explore it, to learn from it, to eventually thrive in it. The cold of space represents the next frontier for humanity. It represents the future of our species if we choose to reach for it. And so the cold, rather than being something to fear, becomes something to embrace. It's the frontier that calls to us. It's the challenge that drives us forward. In understanding the cold, we understand ourselves. We understand what we're capable of. We understand our place in the universe. Before we close, let me address one question that might be lingering. Is there any possibility that we've misunderstood the nature of the cosmic microwave background or the temperature of space? Science progresses by testing hypotheses against observations. Every measurement of the cosmic microwave background by Kobe, WMAP, and Planck has confirmed our understanding. The temperature of 2.7 Kelvin has been verified independently using different instruments and methods. The uniformity of the cosmic microwave background across all directions has been confirmed to extraordinary precision. Could we be wrong? In science, we always acknowledge that possibility, but the evidence is overwhelming and consistent. Future observations might refine our measurements or reveal new details, but they're unlikely to overturn the fundamental insight that space has a temperature corresponding to the cosmic microwave background radiation. This gives us confidence in our understanding. The cold of space is not a mystery or an assumption. It's a confirmed, measured property of the universe. And with that confirmation comes the responsibility to use that knowledge wisely, to explore space safely, to protect life, to extend human consciousness into the cold frontier. The cold of space is vast, indifferent, and eternal. Let me circle back to where we started, to the moment when an astronaut looks out the window and realizes they're about to step into the cold. That moment represents something profound. It's a moment where human consciousness encounters the extreme of nature. The astronaut has trained extensively. They understand the physics. They've checked their equipment dozens of times. But there's still a moment of wonder, a moment where intellect meets emotion, where understanding meets experience. In that moment, the astronaut isn't just thinking about the physics of temperature or the properties of spacesuits. They're feeling the weight of being human in a vast, cold universe. They're about to do something extraordinary. They're about to step outside the protective bubble of Earth and enter the cold itself. It's terrifying and beautiful at the same time. And in that moment, whether they realize it or not, that astronaut is carrying forward a tradition stretching back to the earliest humans who looked up at the stars and wondered. We've always been fascinated by the cold and the dark. We've always wanted to explore beyond the boundaries of the known. The cold of space is just the latest frontier in that eternal exploration. And as long as humans exist, as long as consciousness persists in this universe, there will be people drawn to explore the cold. There will be people willing to brave the vacuum, to face the indifference of space, to expand the boundaries of the known. That drive to explore, to understand, to grow, that's what makes us human. The story of the cold of space is ultimately a story about humanity. It's a story about our curiosity, our determination, our refusal to accept limits. We've come so far from the first humans huddling around fires, trying to stay warm. We've learned to harness the power of atoms. We've built machines to carry us beyond Earth. We've looked at the cold void of space and decided to venture into it anyway. That takes courage. That takes vision. That takes an understanding that despite all the obstacles, the cold, the distance, the danger, it's worth it. It's worth it to expand human consciousness. It's worth it to explore. It's worth it to understand. And so are we, eternally. That search will continue. It must continue, because understanding the universe, understanding the cold, understanding the nature of temperature and time, this is perhaps the most profoundly human endeavor. We are evolved to feel warmth and cold, to seek heat, to avoid cold. But we've transcended these instincts through intellect. We've learned to think about temperature in abstract mathematical terms. We've built instruments to measure the cosmic microwave background. We've sent spacecraft into the vacuum. We've theorized about the eventual heat death of the universe. In doing so, we've taken the sensation of cold, something every human has felt, and transformed it into a doorway to understanding the cosmos itself. The cold of space is thus not just a physical phenomenon, it's a gateway to knowledge, a frontier of exploration, a challenge to human ingenuity and curiosity. And as long as there are humans who wonder about the universe, there will be people who brave the cold to explore it. And it inspires us to venture into it despite the cold, despite the distance, despite the danger. Because the cold of space is calling. The universe is waiting to be explored. And we are here, warm creatures in a cold cosmos, determined to understand it all. The cold of space remains a frontier of discovery, even after billions of years of cosmic evolution. And somehow that makes us human. Thanks for watching. For